So today we finish up 6.5, our study of inequalities, with more about optimization. Before we optimize paths from point to point, from point to line, and line to line, today we'll bring circles into the mix. So we'll optimize paths from point to circle, line to circle, and circle to circle. And just a quick reminder about what optimization is. Optimization is all about one finds a quantity that is either the least possible or the greatest possible in accordance with certain conditions. Like, for instance, we wanted to go from a point to a line along a line segment, and we found that the shortest of all possible paths was along the perpendicular, so that's the optimization there. But today we'll have circles, and this is like our first opportunity to talk in depth about circles, to really use them, though an entire chapter later on is devoted to them. So let's begin with just a few definitions. I suspect you already know these, but let's set them out explicitly. So first of all, a circle is a set of points, because everything is a set of points, in a plane a given distance from a given point that we call the center, of course, right? And a radius is a segment from the center to a point on the circle. So, of course, by definition, every radius in a circle equals every other radius in a circle. And here is a picture to illustrate. So we have a circle with center C, which we will call circle C. That's typically how we name them. We still name objects by points. For circles, typically we name the circle by its center point. So you see circle C, and you see a symbol for circle. There it is. Looks like a circle with a point in the middle, so circle C. And I've shown the radius AC. And the final few set of definitions. First of all, a chord is a line segment that joins 2 points on a circle. So imagine that you choose 2 points on a circle, connect them with a line segment, you've created a chord. And if that chord goes through the center, we have a diameter. So illustrated, you see this. So we have 2 chords. We have the chord DE and the chord AB. They're both chords. They both join points on the circle. DE is not a diameter because it does not pass through the center, but AB is a diameter because it passes through the center of the circle C. And then finally, tangent C. This is a concept that we'll explore in much greater depth in the circle chapter, but it's really a very simple idea. We'll do some work with it here. We say that 2 circles are tangent if they are coplanar and intersect at a single point, which we call the point of tangent C. They're internally tangent if one lies inside the other, externally tangent if neither is inside the other. So on the left-hand side here you see 2 circles that are internally tangent, one inside the other, and they intersect at a single point. And on the right-hand side, you see 2 circles that are externally tangent. Neither is inside the other, and once again, they intersect at a single point. Now, of course, it's a very good question of how it is that we can be guaranteed the existence of tangent circles, right? Like how might we, for instance, construct 2 circles so that they're tangent to one another, and how might we prove that they're actually tangent, that is, that they intersect at one and only one point? That's a question that will be addressed in the circles chapter. For now, we'll just be given that circles are tangent, so the question for us will not arise in this chapter. All right, so let's talk about some of the results that I'll have you prove. I won't talk about all of them. I'll talk about 3 total. But the techniques that are used in the proofs here are just the kinds of techniques you'll use throughout. So I think these are good examples to see. And let me just go ahead and say that in all of these, I think in all of these, almost all of these, that the key theorem on which you rely is the triangle inequality, which might seem like a little bit of a surprise because we've turned our attention to circles, and circles are not triangles, so you would think that this is like a new topic. Perhaps we'll begin to develop like theorems really different, really distinct from what we've seen before. In a way, not really, because our prior study of triangles, and most everything that we've done previously has concerned triangles, will be brought over into our study of circles, both here in this section and in the later chapter devoted to circles. Most everything that we will ever discover about circles will rely ultimately upon previous results that we have proven about triangles. This class really is a class in triangles, even when it seems that it might not be like in the study of circles. It's really triangles. So here's our first result. Let us prove that in any circle, a diameter is longer than any chord that is not a diameter. Okay. Now the first matter is this. We've learned throughout the class that we have to be very careful about what definitions say and what they do not say. The definition of diameter says merely that it is a chord that passes through the center. It does not say that it's the longest type of chord. Okay, it just doesn't say that. Right? That information is not packed into it. Now, of course, I do not mean to say that diameters are not the longest chords. They are, but I do mean to say that it's not part of the definition, nor should it be. Okay, and the reason that it shouldn't be is this: is definitions should be as minimal as possible. They should say only so much as is necessary to pick out the object defined, or object of the type defined, and it shouldn't include any other properties that perhaps could be proven. And we can absolutely prove that diameters are longer than chords that are not diameters. So it should not be in the definition. Okay, so here it is. In our diagram, once again, AB is a diameter, which means that it passes through the center of the circle C. DE is not a diameter, so we wish to prove that AB is greater than DE. And I'll just show you how this is approached. It's really quite extraordinary. So let us connect D to C and C to E. And you might notice then that we have created two radii. Okay, DC and CE are of course radii because C is the center of the circle. And then by the triangle inequality, this will be the only thing that I write because it's what's really crucial here. We know that DC plus CE is greater than DE, right? That just is the triangle inequality after all. But consider that sum, DC plus CE, it's a radius plus a radius, and compare that to the length of AB. Well, AB is a diameter, which means that it's a radius and another radius, so DC plus CE is equal to AB. So AB is greater than DE. And isn't that extraordinary, how the triangle inequality works? All right, the next result is this that I'll consider. Let's say that we have a circle and a point inside that circle, okay? And we wish to go from that point inside the circle to the circle in a way that's optimal, okay? In particular, we wish to traverse the shortest possible distance. It should seem clear that if we have a point inside a circle, we can go various distances to get to some point on the circle, right? We might go through the center point and then off to the other side, like from the point B here in the diagram. That would appear not to be the shortest path. So there are lots of ways that one could go, some shorter, some longer. And what I want is the optimal path, optimal in the sense of shortest. So I have a point inside a circle, and I wish to go the shortest possible path from that point to the circle. I say that one goes along the radius. Okay, that's the crucial idea here. So B was the point inside the circle. I wish to minimize the path from B to the circle. I say that one travels along the radius. Okay, in this case, the radius is AC. So I say that one goes from B to C, where C is the endpoint of the radius that includes B. And how will we prove that that's the shortest path that one can go from B to a point on the circle? Well, this is what we did before. One will consider its relationship to other possible paths that one might go. And B to D is just a representative other path. So what we really need to prove is that BC is less than BD. And how are we going to do this? Well, perhaps it will come as no surprise that I'm going to connect up A to D. And then here's what must be true. Okay, of course, it must be the case that AD, which is the side of one of the sides of triangle ABD, is less than AB plus BD. And I'm not going to write out the whole proof for you. I'll just talk through it with you. So that's true by the triangle inequality. Oops, I spelled that wrong. Silly me. So by the triangle inequality. So by the triangle inequality, TTI, I sometimes call it. So one side of a triangle is less than the sum of the other two sides. But think about that AB, okay? That AB is equal to, that AD is equal to AC, okay? So it's going to follow that AC must be less than AB plus BD. That's just by substitution, of course. Because AD and AC, both of which are radii, must be equal to one another. But think about, and I'll just talk through the rest of it, think about the AC. AC is AB plus BC. So now do that substitution. Or you see AC, right, AB plus BC. So I'll then have AB plus BC is less than AB plus BD, and I can subtract AB from both sides. And I'll get BC is less than BD. And that's the result, okay? That's the result. So notice that it's just the triangle inequality followed by, just like very simple work, mostly algebra. And then the final result, which will also involve the triangle inequality. And again, this is not all the results I'll have you prove. It's just like a representative 3. So let's say that we have two externally tangent circles. Okay, two circles in the same plane that intersect at one and only one point. In my diagram, there's circles A and B, and their point of intersection, that is the point of tangency, is C. And what we wish to prove, and this is the result, and this gets used lots later on in the class, is that the point of intersection, that is the point of tangency, lies on the line through the centers. Okay, that is the line through A and B includes C, passes through C. And how do we prove this? Well, indirectly. So let us assume that the point of tangency, the point of intersection of the two tangent circles, does not lie on the line through the centers. And that's what this diagram is meant to illustrate. Of course, it looks wrong. Diagrams that illustrate the assumption of the indirect part of a proof often look wrong because they are impossible, but we go on the logic, not on how it looks, of course. So A and B represent the centers of these two circles, respectively. C is the point of tangency, and we have illustrated this assumption that C does not lie on AB. Well, what does one do? One creates a triangle, of course. So let us consider this triangle. Well, by the triangle inequality, AB is greater than, said that wrong. AB is less than AC plus BC. So this is just the triangle inequality, right? So AB is less than AC plus BC by the triangle inequality. And then let's ask ourselves whether that could be true. Well, AC is a radius of the left circle. BC is a radius of the right circle. So the right-hand side, which I just underlined, is a radius plus a radius. But now think about AB, and keep in mind that A and B are the circle centers. So as one traverses the path from A to B, one goes along a radius of circle A, then one is outside the circle for just a little bit, and I pointed to it, and then traverses a radius of the second circle to the point B. So AB is a radius of the left circle plus a radius of the right circle plus more. How much more? We don't know, but it doesn't matter. It's more. So this means that AB is actually greater than AC plus BC. AB is 2 radii plus more, and AC plus BC is just 2 radii. So that contradicts the triangle inequality. So that's our contradiction right there. So the line of centers has to lie on the line through the centers has to pass through the point of tangency. And as for the other results that I'll have you prove, they're approached in a similar fashion. Expect to use the triangle inequality throughout. And I really do find this extraordinary. Not merely that results about triangles get used repeatedly here in this initial study of circles, optimization with circles, but it's the triangle inequality in particular that gets used again and again and again. It begins to give you a sense of just how important the triangle inequality is and why it is ultimately perhaps the most important of the triangle inequalities that we proved, and why it deserves the name of the triangle inequality, as if it is the preeminent triangle inequality. In a sense, it is.